Hello, welcome to section 10.2 Notes Ellipses. We are familiar with the shape of an ellipse. We are maybe not familiar with the geometric definition. The definition is that the distance from this point, one focus, to any point on the ellipse to the other focus is constant. So it's written here like that. An ellipse is the set of all points, the sum of whose distances from two fixed points, the foci, is constant. On an ellipse, we call the major axis the longest line that goes from one point to the other on the ellipse. It joins the two vertices of the ellipse, and the minor axis goes from here to there. The center of the ellipse is the midpoint of the vertices. There are two standard equations for ellipses. They both use a number of letters. H and K are the coordinates of the center, and then A is half the major axis, B is half the minor axis. It's important to notice that whether the major axis is horizontal or vertical, the equation changes a little bit. Basically, A, half the major axis, is going to be with the x term if the major axis is horizontal, and it's going to be with the y term if the major axis is vertical. So in this equation, or this pair of equation, it's always very important to look at the denominators and notice where the largest number is. There's also a third number we can look for, C, and C is linked to A and B by the following equation: A squared minus B squared equals C squared. So it looks like a Pythagorean relation. It's not easy to show a right triangle with A, B, and C, but indeed it's called a Pythagorean relation. Here, note how A is always greater than B. It's important to remember that. That's not necessarily true in other sections in this chapter, but it is true for ellipses. When the major axis is horizontal, the ellipse looks like that. When the major axis is vertical, the ellipse looks like this. So notice how here A is measured horizontally. This is 2A. In this case, 2A is measured vertically. So when we try to solve exercises, there are basically two kinds of exercises. Either you are given an equation and you are asked to find information about the ellipse. So you may want to find the position of the foci, you may want to find the major axis, etc. But to do that, you always have an intermediate step. From the equation, you're going to have to find H, K, A, B, and C, and from there, give the information required. The other possibility is that you are provided with information about the ellipse, and you are asked to find the equation. And in this case, again, you need to go from the information given to H, K, A, B, and C, all these constants, and from there, you'll be able to write the equation. So let's see this first example here. Find the standard form of the equation of the ellipse having foci at 0, 1, and 4, 1 and a major axis of length 6. We will always be using this table. You'll need to be very comfortable with this table. It's there at the bottom of your notes for section 10.2, and you'll have it in the quizzes and test. There's only one thing you won't be provided with. This line here will not be there, so you'll need to memorize this line, but not anything else. So let's see how it works for this exercise. Here we notice that the major axis has length 6, and that obviously gives us the value of A, because the major axis is 2A, so A equals 3. Given that the foci are at 0, 1, and 4, 1, we can make a sketch of the situation. This is 0, 1, this is 4, 1. we realize immediately that the major axis is horizontal. Actually, we can already draw an ellipse. Maybe you can see it here. It's not very easy, but the ellipse is there. You can already know that the ellipse is going to look something like that. So it's stretched horizontally, and that means we are in this column, stretched horizontally. That's a key point in solving any of these exercises, being able to know which column we are in. Here we are in the first column, and everything we'll study will use the information in the first column. So, since we know that the foci are at 0, 1 and 4, 1, the center is exactly in between them. It's the midpoint of the foci, so it's the point 2, 1. Now if you look here at the table, the center is HK, so since we know the center is 2, 1, it's pretty easy to figure out that H equals 2 and K equals 1. Also, C is the distance between the center and the foci. I didn't say that earlier, but C is the distance between the center and the foci. You can notice that here. The foci are H plus C and H minus C. So there's a distance of C between the center and the foci. Therefore, C equals 2. It's the distance between 2, 1 and 0, 1 or 4, 1. Now that we have A and C, we can use the Pythagorean relation. It's written here, and we can find B. A squared equals B squared plus C squared, so 9 equals B squared plus 4, B equals root 5. So I found A, B, C, H, and K. I can just copy the standard equation and plug in my values for H, K, A, and B. You may notice that we are not using C in the standard equation, but we still need to find C when we are solving exercises like that, because we needed C in order to find B. So the answer is x minus 2 squared plus over 9 plus y minus 1 squared over 5 equals 1. Second exercise, sketch the ellipse given by 4x squared plus y squared equals 36. The standard equations in both columns are always something equals 1. So here we need to divide by 36 to have that. The equation becomes x squared over 9 plus y squared over 36 equals 1. 36 is bigger than 9. That means 36 is a squared. It has to be. So a equals 6, and 9 is b squared, so b equals 3. Which column are we in? Are we in the first column? Are we in the second column? We said that a equals 6, so a is with the y term here. It's y squared over a something. So that means if I compare my two columns, we are in the second column, because the y term, y minus k squared, is the numerator of a squared. If the numerator had been larger here with x, then we would be here. A is with x. So in this case we are in the second column, and since it's x minus h squared, we see that h equals 0, y minus k squared, it's k equals 0, so the center hk is 0, 0. If we look at the equation for the vertices are at h k plus a and h k minus a. So with our findings that h and k are 0 and a equals 6, we can find that the vertices are at 0, 6 and 0, negative 6. Also, because b equals 3, the minor axis has a length of 2b. So the minor axis has a length of 6 altogether, which means that our ellipse is going to go through the points negative 3, 0 and positive 3, 0. The center is the origin, so here's a tiny sketch of my ellipse. The next exercise is a bit longer. We'll read question A only, and then we'll read question B and C later. Write the ellipse's equation in standard form. X squared plus 4y squared plus 6x minus 8y plus 9 equals 0. Quite obviously, this does not look like our standard equation. We need to make transformations. What are the steps to do that? Well, let's have a look. X squared plus 6x plus 9 equals negative 4y squared plus 8y. What did I do? I just separated the variable, all the x's on one side, all the y's on the other side. X squared plus 6x plus 9 is the square of x plus 3. So I can simply write this as x plus 3 squared. It was lucky that it's a square. If it's not a square, like negative 4y squared plus 8y, I need to complete the square. You need to be very comfortable with completing the square, because we do that not only in this section 10.2, but also in the other two sections. To complete the square, I start by factoring negative 4, so the right hand side of the equality is negative 4 times y squared minus 2y. This should be a y. Negative 4y squared minus 2y. We add 1 and we subtract 1. This is completing the square. So now I have y squared minus 2y plus 1, which is equal to y minus 1 squared. The negative 1 here is left over. It stays there. And we don't want to have it inside the parenthesis, so if I distribute the negative 4, I'll have negative 4 times y minus 1 squared plus 4. Now that I did that, I can move the y term back to the left side of the equation. X plus 3 squared plus 4y minus 1 squared equals 4. And divide by 4 in order to have equal 1. So here I am, this is the standard form of the equation. Question B is find the center, vertices, and foci. So now we're going to be using the table up here. First we need to realize which column we are in. The largest denominator is 4, so that means 4 is with x. We are in the first column. A equals 2, B equals 1, H equals negative 3, K equals 1. We can extract these informations immediately. We have A and B, we can find C using the Pythagorean relation. 4 equals 1 plus C squared, and therefore C equals root 3. With all of that, it's pretty easy to write the center. It's HK. So negative 3, 1. Let's move this here. So the center is HK, so it's negative 3, 1. The vertices are H plus A, K. So H plus A, negative 3 plus 2 is negative 1. And the second coordinate is K, so 1. Negative 1, 1. H minus A, K, is negative 3 minus 2, negative 5, 1. So this is negative 5, 1. Same with the foci. The foci are H plus or minus C, K, and I can easily find that the coordinates of the two foci are negative 3 plus root 3 and 1, as well as negative 3 minus root 3, 1. Question C asks to sketch the ellipse, so here it is. I have the two vertices, negative 5, 1 and negative 1, 1. I could figure out that this point is tangent to the x-axis. And there's another point here that I could have shown. Since b equals 1, it means the minor axis is equal to 2. That means this point up here has coordinates negative 3, 2. Ellipses have an interesting property that we need to understand. The property is represented here. Imagine this was a blue wall and you were standing at one of the foci. If you roll a ball and it just rolls straight until it hits the wall, it will bounce on the wall and go to the second foci. And this works wherever you roll the ball. Let's say I roll the ball in this direction, it would bounce here, and then it would go straight to the foci, to the second focus. There's applications in acoustic designs, machine gears, and medical devices. Also, paths of planets are elliptical. So the path of a planet's orbit around the Sun is also an ellipse. The Sun is at one of the foci. This is important to know. The Sun is at one of the foci. The closest distance to the Sun in an orbit is called the perigee, and the furthest distance is the apogee. So for the next exercise, this is a sketch of the situation, but it's really not to scale, so we'll have to be careful with that. The Moon travels about the Earth in an elliptical orbit with the Earth at one focus. The major and minor axes of the orbit have lengths of 768 and 767,000 kilometers respectively. Find the apogee and perigee from the Earth's center to the Moon's center. So I put the Earth at one of the foci, I drew an ellipse, but obviously in reality the Moon is almost turning in a circle. It's certainly not that close to the Earth, and it's certainly not that far to the Earth at the other end. Since we have the major and minor axis, we can simply divide by 2 to find A and B. And when we have A and B, we can use the Pythagorean relation to find C. C is 20,179 kilometers. Remember how C is the distance between the center and the foci? It means that C is this distance here, from the point E to the center. It's only 20,000 kilometers, so compared to these huge distances, it's really small. So that should actually be a tiny, there should only be a tiny space here. Now the perigee, we're just going to subtract this difference, because the distance A is all of that. So if we subtract C, we'll have this distance, which is the closest distance between the Earth and the Moon, and the answer is 364,224 kilometers. Now, how can we find the largest distance between the Earth and the Moon when the Moon is here? This from here to there will be A. It's half the major axis, and we have to add C, we have to add the 20,000. So the largest distance between the Earth and the Moon is 404,582 kilometers. At the very bottom here you have the summary that I showed you, and you will have this on the quiz and test, but you really need to be comfortable with how to use it. Thank you.